All right. Well, I've got promptly right at 2 o'clock Central Standard Time, so I'll start in, give you guys a little idea for background as well. We do these webinars the last Thursday of each month. We are taking a break in July, so the next one will be the last Thursday in August, and that's going to be held on the topic is best practices for segmental retaining walls, which today will kind of lead right into that best practice discussion. So I appreciate everybody taking time out of their day to log in and have a good discussion. I guess it's going to be a little one-sided since I'll be doing all the talking, but as we're going through, feel free, like I said, type your questions in that chat box, and I'll answer those as we go through. And give you a little background, my name is Kyle Hurd. I'm one of the engineers here at Allen Block Corporate. We're located in Minnesota, so I guess the furthest away we have, I guess, BC and Virginia. We're kind of, Minnesota's right in between, so I guess the award can go either direction today. So, but we've got 5 engineers here in our office that our biggest side is training. So at any time, if you have questions on retaining walls in general, feel free to reach out to us. That's what our staff is here for. It's a resource for really the engineers around the country and the world. So, but today, what we're going to be doing is running through that basic engineering kind of practices or engineering principles. So the reason for some of these training events is really to raise the professionalism within our industry. We want to build really a good base with the engineering principles on segmental retaining walls, because the industry is really only about 30 years old. So, you know, the new engineers, I put myself in that category. New engineers coming out of college and getting into the working world, they may not understand or know segmental retaining walls is an option. It still, a lot of times, is not provided in school. So, education-wise, feel free to jump in on these, share the links, but we really want to, our objective is to make sure that everybody is familiar with segmental retaining walls and how they work. And then we're developing those proper construction methods, and this is really that need for formalized training. Go through. So I had mentioned best practices. This is actually the first page out of best practices that you'll discuss more in depth in August if you attend that. That best practices, I believe it's last Thursday of the month is August 30th, if I remember looking at the calendar right. And this really is to start the conversation on having the wall designed early on in the process. Really, in today's world, we almost do like a performance design, and this best practices is really towards a initiative called zero wall failures, and that's really what we're going for. Is we don't want a wall to fall down. Everything we want to stay vertical. If a segmental retaining wall falls, it's really a black eye for the industry. So, if you're interested in that, like I said, feel free to sign up for that once this is done, or check your technical newsletter. We'll also send out a reminder email the week of that training. So, in the interest of segmental retaining walls, really, this kind of backyard modular block, 4-foot high wall, this is probably 90 to 95% of segmental retaining walls around the world. It is kind of the bread and butter. Small residential commercial work, but to give you an idea, modular block can be used for anything from a 2-foot high wall to 40, 50, 60 feet. There really isn't a limit to it. It comes down to, obviously, the land space or availability and the cost for those projects. So my tallest, to give you background information, my tallest structure is down in Tennessee. That's 72 feet from bottom to top, tiered back 3 times. So with that, there's also luxury apartments directly above those, 15 feet actually measured from the front face of the block. So very tight site, but we know that these walls work, and they can last a lifetime if we go through and really understand the design properties and then, of course, the construction of those. So segmental retaining walls, definitely anywhere, it kind of sky's the limit. There isn't a max height to a modular block retaining wall. We'll talk about different design reinforcement options through today. To take you through a couple additional products from Allen Block is a fence system. It is a modular block fence system again, but this is really privacy screening, sound abatement. The biggest one being sound, because it's a concrete fence. So roadway noise, new developments, or even existing developments that have maybe like an old wooden fence that's falling down, that they're looking to, screen out some of that site-wise and traffic noise. So this would be a product that would be engineered, and you can work with our engineering department. The bread and butter would be somewhere between, 6 feet and 10 feet would be kind of that normal number for height-wise, but we do have fences as tall as, mid-30s, 36 feet, for instance, out in New Jersey. So, John, that actually wasn't in Chattanooga, but it was, I believe, Brentwood, so just outside of Nashville. But apparently there's more than one 72-foot high wall down there in Tennessee. So the last product I do want to share with you is Courtyard. This is more of a DIYer. This is a homeowner contractor driven. It's not engineered. This is really your outdoor living. So seating walls, patio surrounds, outdoor kitchens, grills, that sort of thing. This is adult side Legos. So if anybody wants to really play with Legos again and I guess not get looked at strangely, you can always go to one of our distribution locations, and if you've got a small little project, this literally goes together real quickly. But really, your outdoor living, taking those rooms into your backyard. So the Allen Block advantage is really, I'm not going to bash competitors through today. Really, we understand as an industry that when one modular block works, they pretty much all work. I mean, there's slight differences between blocks, and there's features and benefits to every one of them. And already, if one wall fails, a modular block wall fails, it's a black eye for everybody. So from our stance, we really do not want to see a wall fail or fall down or have issues with it. So our advantage is really, I've already mentioned there's 5 engineers here in our office. You can reach out to us at any given time. Regardless of what product you're looking at or using on your retaining wall design, feel free to use us as a resource. We do retaining walls every day. We work with engineers or professionals around the world to help assist on your projects. So there isn't a cost to any of our services, but use us, use our local resources. We do training with our technical reps around the world as well, so that they can bring that technical side right there to your office. And stop by and help you out on your project as well. And then on that training level, there is a certification program. If you didn't know, there's 2 nationally accredited certification programs. There's the Allen Block certification course, and there's the SRW installer course from the NCMA. Both of them are pretty much the exact same program. They have 3 different levels to them. Level 1 being they've gone to the training course and they've built 1 wall. Level 2 being experienced is 5 additional walls after that first. And then Master Wall Builder is really 25,000 square feet. So they've installed a large amount of modular block. So for instance, that 72-foot high wall, and hopefully John too, the installer was a Master Wall Builder, somebody that had used the product, used the block over and over again. Mainly because we don't want, I always say, Joe with a pickup truck and a shovel. Make sure that they aren't the low bid and they're not coming in and building this wall without the experience level. So we can qualify contractors from the engineering side, and you can do that through those programs. I usually ask, since you guys don't have audio with me, but I usually ask if you know the difference between dry cast and wet cast concrete. Being that I'm the only one talking, I'll give you the answer as well as asking. Hopefully, Andrew, you get audio up here shortly. But the wet cast and dry cast side, Wet cast is exactly what it sounds like. That's coming out of a cement truck, for instance. It's a poured wall. Or, for instance, it's poured into a mold, and then that mold is typically stripped off 1 or 2 times throughout the day. And when that mold is stripped off, then you're making a block every time it's stripped. So you might be manufacturing, 2 blocks per day per mold. And if you have 2 molds, you're at least, 4 blocks. Dry cast concrete is the exact same ingredients. So you've got your concrete or your Portland cement, your aggregate, but you have just enough water to kind of saturate or hydrate the cement, and you're almost creating a sandcastle is what you're looking at. So what that's done, that material is put into a mold box, and then that mold box comes down and consolidates, compresses everything into really a block, and then it's stripped off. Well, typically you're making 2 blocks face to face. That's how you get that split face block, and you have a cycle every 10 seconds. So you're making technically a block every 5 seconds that goes into a kiln and then comes out the other side at your compressive strength or above. So what you're looking at there is you can manufacture dry cast concrete in the tens of thousands of blocks per day, so you get tens of thousands of square foot per day. And then on wet side, you may be limited to 10, 20, 30 square feet per day. So production side is a lot slower. Large projects may eat up a lot of inventory on the wet side. So you have to think through that as well. When it comes to the specifications that we follow on the production, you're really looking at that ASTM 1372 and 1262, and that's what's highlighted here on this slide. That compressive strength 3000 psi, many manufacturers are well above that these days. I can speak for here in Minnesota, our manufacturer their standard block is double that. They're just above 6000 psi. Absorption, you're really looking at, if we turn that into almost a percentage, you're typically under that 8%. Most manufacturers will be somewhere between 1, 2, and 3%, to give you an idea. So very low absorption. And then unit strength, shear strength, that sort of thing, 1,400 pounds per block, which I'll explain here shortly what Allen block's shear strength is and where we sit. And take you through some of the products. The different collections. That AB collection is kind of that split face block, Europa being a tumbled product, and then Fieldstone being kind of a natural stone or a outcropping product. So I'll show you kind of each of these as we go through. And Aztec is really kind of the new product, new from Allen Block here in the last couple of years. It's really a smooth face, kind of textured block. So it's getting away from that split face. We've heard kind of coast to coast that everybody wants a different aesthetic, a different look, and that's what this product line is really bringing to that, which I'll show you some pictures here in just a moment. But that AB collection, we've seen it for quite a few years. You had that tri-split block in the 90s, and now it's kind of that straight-faced, still split. This can be residential, this can be commercial, this can have fences above, parking lots above, slopes below it, you name it. It is both a backyard and a commercial product. Then when we get into blending that with multiple size blocks, we call from Allen Block the Ashlar pattern. That Ashlar pattern wall can be, again, large commercial jobs like this. This is in Beaverton, Oregon. This is one land bridge, so it's a double-sided wall going to a new development. Now this new development is all filled out and it's retail commercial use, and there's dozens of these land bridges all across that area. But again, the pattern walls, it doesn't have to be the 4-foot or 6-foot backyard residential. It can have large roadways or commercial roadways above it. This is an entrance ramp to a freeway. Or getting into that Europa collection. That is really kind of that tumbled product. So you take the same block and you beat it up more or less, and it gives it that old style look. So whether that's, again, residential or commercial work, uh, whether it's the Cincinnati Zoo or a commercial property like this. Uh, that product again works universally there. And then the field stone. That is really that natural stone kind of look, that chiseled rock. It does have two different anchor units. You've got a short anchor and a deep anchor. And where that comes into play is so that you can transition from, remain as a gravity wall. So if we were on a 27-degree friction angle soil with a roughly it's about 12 inches measured from the front face, we're able to get about 3.5 feet before we have to use geogrid or some sort of reinforcement option. If you switch to the deep anchor unit, you can almost hit 6 feet. So you can see if you have a tight site constraint, fieldstone can definitely be an option. But I always recommend reaching out to your local rep, technical rep, or giving us a call to see about availability because fieldstone may not be locally to you. But again, residentially, commercially, you name it, the products don't have that limitation to them. So really this is kind of a mix between that outcropping block, again, residentially, but upwards of about 8 feet when it's turned over there and butting up to the house on the one side. And then I had mentioned wet cast. This is actually a wet cast product right here in Minnesota. Actually, is where this is, off Lake Minnetonka, if those of you have ever visited beautiful Minneapolis. So this is a wet cast product, or a wet cast face, with our fieldstone line. So we do have both ends of the spectrum. We've got the dry cast and wet cast, and really just kind of looking for that aesthetic or that solution for your clients. And then the Aztec. That Aztec is really, here in the last couple of years, been very new to the industry. And it's looking at the same, this is the exact same AB Classic block right here. It's just we put a division plate in between in the mold, so we no longer split two blocks apart. We have a division plate there that gives it that texture. So nothing new on the manufacturing side, but aesthetically it looks completely different. So a project here in Cincinnati, Ohio is actually where this one is. So all 4 block pieces put together to create that. And then if you want to incorporate split face block into that split or that smooth face, the Aztec line, you can accent different things and show a lot of different combinations. And all those blocks are exactly the same. You can see here the base course under this wall is all AB Classics, which is our split face block. So they work together. It's still that 6-degree block and works universally through there. So very straightforward. That's as much as I'm going to talk about the product line itself. So I appreciate you taking a little time here to run through that. To give you the history, Bob Allen Gravier is who started Allen Block. He is the founder of Allen Block back in really the 80s when all modular block walls began. They all began right here in Minneapolis. Whether it was a long winter and everybody just was bored and came up with a block design, Bob came up with his and moved forward. So I always joke and say this is Bob's first Allen Block is what we're looking at here with the pyramids. So obviously not the case, but this is dry cast concrete. It's a mortarless construction. That's what the pyramids are built out of, is our dry cast concrete. Made a little bit differently, but same concept. So we know that dry cast concrete lasts the test of time, and we can prove that with the pyramids. So Bob did get beat up a little bit early on in the industry, mainly because he had a block that was hollow, and he had a front lip configuration to the block, and he didn't have pins. So those were things that the industry instantly started off. You need to have a solid block and pin system. Today, we've evolved to a point where almost every manufacturer nowadays has a hollow core system, or they're hollowing out the core to really increase performance and shipping, different benefits to that. So So I can always say that Bob was, I guess, a genius for starting that path and sticking true to it. But he did obviously have some issues at the very beginning and hurdles to come over. But that's what an alum block is kind of that hollow core system. It's got back wings to it, cross-section view. But the huge benefit to segmental retaining walls over like a rigid structure cast in place or masonry walls or anything like that is the ability to bend and not break. I do have some animations that are built in here, but they aren't working with this platform. So really what we're looking at is a segmental retaining wall that can bend and change with frost. It doesn't have to go down to frost depth. So in Minnesota, 42, 48 inches, we don't have to bury block down there. We can stick to our 6, 8 inch typical buried block amount. But overall, I've been told by multiple people in the industry or kind of around different areas that they've always told me there's two types of concrete. There's concrete that cracks, and there's concrete that's going to crack. That's just how things are. Well, modular block has kind of those cracks built in. That's what makes them able to flex and move and aesthetically still look good, is we're not seeing those fractures in the block itself. Same with your interlocking concrete pavers. It's the same concept. They can flex and move with the ground. So that's why there's such a large market for those things. I had mentioned the lip notch configuration. That's how the blocks interlock to one another and give it that built-in setback. But it also has a superior shear key. So you have to shear off this lip right here at the top in order to fail in shear, which I'm going to show you at the end of the presentation. There's only one project that we've ever had that actually sheared the lip of the block. So with that lip notch configuration, we have predetermined setbacks. So there isn't, I had mentioned pins. There aren't alignment pins or anything like that for the contractor to use. They stack block and pull the block forward. What you'll notice here is a 3-degree block has a deeper notch on bottom, where that 12-degree block doesn't have as deep of a notch. So you get more batter in the wall. So that's how we can easily switch between two different products or two different blocks for depending on the application. And it's all preset, predetermined before it arrives even to the construction site. And then segmental walls, it needs really your drainage. Right down here, I'm going to point out that drain pipe at the bottom, that needs to be vented to daylight. So commercially, if you've got a storm sewer or if you've got slopes below the wall or something like that, that you're able to route that around and come out to daylight, you do need it vented every 50 feet linearly along the layout of that wall. You can come out through the face, which is a very common application. When you do that, raise that drain pipe up, you want to make sure that this material down here is used as kind of like a road-based material. That is it's got fines in it, it compacts really well, it's going to be impermeable is what you're looking at, so that that drain pipe can come out. And really, this is only for incidental water, but we want this almost like a shelf. Water comes down and then navigates out. So that drain pipe should stay dry, and as long as routing water above the wall around it rather than through it, it should stay dry 99% of the lifetime of that structure, or that wall. So, and then filtration. I actually want to talk more about filter fabric along the back side here. In the past, the industry has had vertical filter fabric. When the NCMA released their 3rd edition, filter fabric vertically is more optional. And really from the design side, we don't want to run filter fabric vertically because it runs the risk of clogging. And that filter fabric could be really your landscape fabric is what I'm referring to, because there are other geotextiles on the market that you could use, like embankment protection fabric, something that's got properties to it, engineering properties, puncture strength, etc., that we'd use in water applications. We would use that vertically then to separate soils and make sure that we don't have moving material. But vertical filter fabric, just offset your site soils and your clean rock is not required. And really you're only looking at using that filter fabric horizontally across the top to separate, your topsoil from your infill soil or your clean rock. That's really where the industry has been and then evolved to at this point. Again, that was more in the kind of 2009 on from the third edition from the NCMA. And then getting into, I had mentioned a solid block. Bob didn't have a block that was solid when he began. Really, at the end of the day, when you fill an alum block with rock, with your what's called wall rock, your aggregate, your 3/4 inch clean, you get very similar weight. So there wasn't a benefit in mass-wise for a retaining wall, since it's all based on mass, that we couldn't use alum block with our rock in the core, equivalent to kind of that solid block. So with that hollow core, there are some benefits to it. I'll call it features and benefits here. But superior drainage, it has technically a secondary drainage field. Even though that is for incidental water, we would hope that any water that does come through there, that's already captured before it even gets to the wall. But the biggest thing is faster drying. Really, faster drying helps in the efflorescence category, so there's less efflorescence. Since any concrete or any concrete product can have efflorescence, I always think of kind of brick on building, because brick's red and you always see the white staining from water. That is, efflorescence coming through the product and then staining the face, so that the chemicals within the product itself actually kind of push through with that moisture. So if the block stays dry or dries faster, you have less moisture pulling through and therefore less efflorescence. And then I already mentioned production, labor, and freight costs. You can ship a hollow core block further for less, is what that comes down to. So it really opens up the production and servicing different projects with that hollow core. So I'd mentioned most manufacturers do have a hollow core system within their arsenal these days. And these are kind of those reasons why. So to really start talking about the engineering side, first and foremost, I do want to point out that those aren't goats up there on the hillside. Safety first. I always joke here that OSHA was not on this job site since they're, excavating this wall up here. But most likely, I don't know if the next picture was everybody was sitting down here in the bottom of the hole or not, but make sure on your commercial job sites that obviously OSHA has followed our OSHA-approved methods. But even back in, you're looking at a cross-section renovation of the Great Wall of China. The Great Wall of China, when they built this, you can see that they have a thicker base at the bottom. Therefore, they already knew that the pressure is highest at the bottom of the wall. So it's very much like a swimming pool. You dive to the deep end, you get more pressure on your head. That's the same concept for soil, just to a higher degree. So the deeper you are into that material, the more pressure is exerted on your retaining wall. So I'm going to go over kind of the basic soils. I'm a geotechnical engineer, so we're not going to go into the specific properties of soil. I'm actually going to use the friction angle. So I'm going to use the friction angle as the natural angle of repose just for today's discussion. And what I'm meaning there is the natural angle of repose here is how high that material cones up. Sandy soil is going to cone up higher than like a clay soil that's very flat and smooth. If you have gravel, it's going to cone up a little bit higher. Once you add compaction and moisture contents, etc., that's how you get your internal friction angle. That is your calculated or your tested value of that soil, and that's what we use on our retaining wall designs. So again, I'm going to refer to it in today's conversation. We're just kind of going off of that natural angle of repose. So if that natural angle, cones up higher, for instance, the sandy soil has a higher cone, therefore the triangular wedge that's pressing on the back of our retaining wall is smaller. And that leads to our lower pressure. Less soil, lower pressure. Then this clay soil that kind of has this nice large wedge. That's going to exert more pressure on the back of the wall because you have more mass or more driving force there. And that's all based off that active pressure. So let's talk a little bit about batter real quick and how that calculates into our soil. So if we have our vertical wedge that we just looked at there, in our sandy soils, we've got that vertical wedge. Well, if we take batter of the wall into play, we reduce that wedge. You can see here we reduce it by almost 50%. So a smaller wedge, therefore less pressure again. So that's why many manufacturers kind of around the world have products that are somewhere between 3 and 12 degrees. Most projects are actually dialed in closer to about that 6 degrees, somewhere between 4 and 8. So, excuse me. So having those products available and able to engineer-wise, we're able to reduce the amount of pressure with that batter. But at the same time, we're looking at how much space does that take up. With every setback a block, you lose some real estate above the wall. What's that balance? In a 30-foot or, the 72-foot high wall, that has a tremendous amount of batter, especially in 3 tiers, being, upwards of about 25 feet a piece. So you do have to take that into account. My animations here won't work. What I've got is I apply that wedge here to the wall, and my guy falls down. I take that wall and then I push it back into the hillside 12 degrees, and my guy stays vertical. Very similar to what we're looking at here. So if we look at a 3.5-foot high wall, our active earth force, you'll see 217 pounds. Just with the batter itself, it reduced it 25%. And you can also see your Ka value. So that's our active earth coefficient. That also reduces. So as soon as your Ka value reduces, therefore you have less pressure. And that Ka, I'm about to show you the equation just in a couple slides here to really kind of dive into it. So looking at our free body diagram, we're looking at my example wall here is about 3.5 feet and 12-degree batter is what we're looking at. So when we look at that and we throw it into our equations, that active earth pressure coefficient is right here. This Coulomb equation that's dialed in to include the batter. Well, B stands for batter, F stands for friction angle of soil, and then I stands for your slope above. So on the design side, if you change the batter of the wall, the soil behind it, or the slope above it, you change the design of that wall. So increasing the batter will actually reduce our coefficient here. And that would be the same concept if we increase the friction angle, we're also going to reduce our coefficient. Since our mass or our resistant force is all on weight on a gravity well, we're looking at that right here. We drop that into our factor of safety. So 1.9 and 1.5 being the industry standard minimum in sliding. And if we look at our overturning resistance, same concept. We're still looking at our mass. Our resistant moment is all due to weight. And when we look at that in overturning for almost 3.5-foot high wall, we've got a 2.6. And 2.0 is our industry minimum for overturning. And other than for the overturning and sliding factor of safety being 1.5, sliding does not account for any kind of passive pressure in front of the wall. So really most walls are, well, I should ask you guys, have you ever seen a wall that's failed in sliding? It's not too common. Most retaining walls are going to fail in overturning before they do in sliding. But in that sliding factor of safety, you also have to remember we do not apply, or even in the technically the overturning. We don't apply any passive pressure in the segmental retaining wall design. So that's an added benefit to the system. So if we look at a gravity wall max height, okay, let's look at 27-degree clay soils. Come across here to that 6-degree. Really, a 3-foot high wall. As soon as you get above a 3-foot high wall, a 12-inch deep block is at its capacity. Now you have to increase the depth behind that, whether you have an 18-inch, 24-inch, or you start getting into an alternative reinforcement like geogrid, no fines concrete that we're going to talk about here shortly. But just keep that in the back of your mind, because most ordinances are, engineering isn't required until 4 feet. Well, I'm guessing you can probably drive around your area and you can find modular block walls that are slowly beginning to overturn, right? And they're probably right around that 3.5 foot high wall that, geogrid possibly wasn't used behind there, or some sort of external load was applied to that wall. So keep that in mind. It's kind of that 3 foot. Even in good sandy soils, I'll call 32 degrees, kind of our sandy material. If we come down here with a 3-to-1 slope above, with that 6-degree product again, right about that 3 foot mark. So 3 foot is oftentimes for a 12-degree or a 12-inch deep block that max height before you actually need to start talking about reinforcement. And this is before even adding surcharges, any kind of load above that wall. So if our gravity wall with a 12-inch deep block doesn't work, you can create a taller wall with what we call a double block wall. And with Allen block, you can actually take this back block here and you can spin it around so the backs are touching, and then flip the block over so that the lip is actually down. And what that allows is the block stacks up in the same batter as what you've got right here on the front face. So what we're doing is actually we're increasing the depth of that block to 24 inches rather than 12. So then we can go taller with our gravity wall. But if a taller gravity wall or a double block option doesn't work for you, maybe you can use no fines concrete. No fines concrete is it's a permeable concrete mix. So it's a mix without sand. So it allows water to drain through it. You can see here it's free draining. What that allows you to do is you can create a block that's any depth that you need per the design. So if any of you are familiar with large blocks on the market, this can definitely be an option for you as an alternate. You're technically what you're doing with a small block with no fines concrete is you're creating a big block on site without that manufacturer's cost. So at the end of the day, typically, and I always say somewhere between 12 and 15 feet, there starts to be a swing where if you get above 15 foot, it might be a cost-effective solution to use geogrid rather than no fines concrete. But for the most part, 15 feet and under, you might look at an alternate to a large block design, and it could be upwards of savings, even close to about $10 a square foot, is very common kind of across North America here. So those are other options, and you can design no fines concrete within our design software that I'll explain a little bit at the end before we leave. But where this actually comes from, I didn't see anybody sign in from Australia, but maybe they're here now. But no fines actually comes from our Australian partners. They've been using it for upwards of 20, 25 years is where that comes from. And so it's really a dry mix. It's not a slurry. You can see the guy here is pushing the mix down the slide to make sure that it gets all the way down. And then you're able to stack up really 2 blocks at a time and pour behind, fill the cores. And again, you're creating that mass is what you're looking at. You can do it on new construction. You can do it on existing timber walls or existing any retaining wall. You can face it with something different. Now keep in mind that this wall is actually designed so that if this timber wall wasn't even here, this wall has enough mass already to resist all the pressure and the surcharges from the alleyway above. So, but you're really just kind of sealing up this timber wall into the hillside. So regardless if that deteriorated, you still have enough mass there to resist that. So having that higher aesthetic or bringing a new aesthetic to an existing lot can be done with that no fines concrete. And then really using it as, on this one, if you don't have access for the truck, that skid steer can bring it to the backyard and dump it behind the wall. So this wall actually has no fines behind it, but as it curves around the house, we actually transition to geogrid. So it doesn't have to be no fines for the entire span. It might only be one small location that you might need to switch over to that alternative reinforcement. So I'd mentioned it's very dry. Some places, if you get into kind of the western side, you get, Portland, so Oregon, Washington, Idaho, that area, we refer to no fines concrete as stabilized aggregate. And the industry has really started using stabilized aggregate more than no fines concrete, mainly because the inspectors, as soon as you hear concrete, they're thinking slump tests and compressive cubes and that sort of thing, where this is really an aggregate that has a little bit of cement in it to solidify and hold up. It's a very low compressive strength. You're probably talking, 800 to 1200 psi. It's not meant to be in compression. It's all the force is laterally on it. So it's really just to increase that mass. But you can see here he's sweeping off the blocks because he's getting ready for the next lift, where he's going to stack up 2 more blocks, and then they're going to pour alum block or pour no fines concrete in to the cores and then behind the block. And he actually used plywood to make sure he didn't have any spillage here onto the soil. So really there's no compaction of the material. You don't have, you increase your efficiency on labor. So even though your material cost goes up on a project, your labor cost actually goes down. So that's why I say that 12 to 15 foot mark is kind of the break-even point. You can actually, no fines concrete might be very similar to a geogrid design. Up to about that 15 foot. Our tallest no fines wall is actually one that I had down in Georgia. It's 26 feet. They couldn't make anything else work. Geogrid couldn't extend into the hillside, so that was kind of their option, and it was still cost effective compared to a rigid structure, sheet pile, soil nails, that type of thing. So, so definitely options there available to you. And then we've got a no fines chart. This chart only goes up to 10 feet, but I had mentioned you can do a no fines concrete design within AB Walls, which AB Walls is our design software. And overall, that design software provides you those calculations and the full package of what you need. But here you could use a quick reference. Bill, you asked what was the depth of that concrete on the 26-foot high wall. I believe it came out to be 40% the height. So without grabbing my trusty calculator, I think that's right around 10 feet. So is the overall depth behind that. But very similar, a rule of thumb, you're probably somewhere between 40%, maybe 30 to 45% is very common for most of them. So that's a no fines concrete mass. So we looked at gravity walls, double block walls, no fines. Really, we're going to talk now about soil reinforce, so geogrid. And I go right back to actually the Great Wall of China here. They use branches actually to reinforce the soil. So that is technically a natural geogrid or a geotextile. And so the history of geotextiles really began back then, very similar to our mortarless concrete. So the components of our walls, we need mass. That's really what we're looking for. We need that mass to resist any kind of lateral pressure that we've got, or that active force that's pushing on it. So if we look at, for instance, a cross-section, if we're using geogrid reinforcement, we've got these soil layers coming back typically, well, your minimum length is 60% the wall height. But we're technically, what we're doing here is we're reinforcing this mass. This soil is now our new mass that we're going to resist all those pressures. And this acts as a coherent mass. So the block isn't independent from the grid, which isn't independent from the soil. They all work together, very similar to your concrete rebar designs. Rebar reinforces concrete to add that additional strength to it. So here we're reinforcing the soil with our geotextile. With that geotextile or geogrid, typically a vast majority of grid on the market is uniaxial. So that means it has strength in one direction. It needs to be rolled out properly. And that is something that we emphasize in the contractor training courses that I had mentioned earlier. Make sure that the contractor rolls out the grid appropriately. If it is a uniaxial grid, you'll have strength here that you'll roll out perpendicular to the wall. But if you look, you actually have only about 60% that strength in the opposing direction. So if they rolled this out incorrectly and we need that strength, we now lost that and we could potentially have an issue long term. So there are biaxial grid on the market. This is typically, most biaxial grid is used for retaining walls 6 feet and under. There's some geotextiles that are biaxial that we use in bridge structures, but that biaxial grid I look at as, I always call it the drop and kick method. You can roll it out with the wall. It's going to have strength in both directions. So just know on your projects which grid you're specifying, which grid the contractor actually orders and delivers to the job site, and have that, make sure that's inspected, especially on those larger commercial jobs. So, all right. So I mentioned really quickly connection earlier. With that hollow core system, you actually increase your connection capacity because what you're doing is your connection comes from your interlocking or your interaction of your rock with geogrid, your material with geogrid. So hollow core systems actually have a superior connection strength to it. And it's what we're referring to here as rock lock connection. If I were to look at it as, a hollow core system, it's continuous at the face all the way through. So it's our spiral bound notebook. Think of it as it's harder to pull this page out rather than if you have, and I'll use the pin in this case, if you have any kind of point load system, then it may be easier then to pull this out. So that hollow core is, again, why a lot of manufacturers have gone to hollow core block over solid block over the years. And then I already mentioned continuous at the face. This rock is going to fall and interlock between these typical holes on geogrid are 1 by 1, and we're using like a 3/4 inch clean. And then you pull the grid back to make sure you don't have to tension it, but just make sure that it gets all of the slack out of the geogrid itself. And then that grid, getting away from the face, interacts with the soil around it. So it's going to have interaction right here. And really maximum spacing for the industry is that 3 courses. Best practices, which we're going to talk about at the end of August, the industry is really pushing for that 2-course spacing, or every 16 inches vertically. So to determine if our mass is sufficient or not, what I'm going to do is show you really our external and then internal calculations. So I've got some animations here, but I'm actually going to jump past them. Our sliding is one component for external that we're checking. Again, we don't take into account any kind of passive resistance in front of the wall. Overturning failure is that whole mass wants to overturn. Bearing, so what kind of foundation soils are below the wall. And if we have a bearing issue, most times we can compensate to this to bringing in select fill on our sites. And then external stability also would include a global failure. If this wall was designed perfectly, but the entire slope kind of fails and goes for a ride, that retaining wall is also going to kind of slide down that hillside. So those are our external. How tightly our soil mass holds together, or tightly knit our structure is, That's again, like I said, concrete and rebar. But that's the same concept here, is the geogrid working with the soil itself. And we do check internal calculations, which would be rupture. So how strong is that geogrid? We look at soil pullout. Now if you think of this as a failure plane or a line of maximum tension that goes up, you need to make sure that the geogrid extends at a minimum 1 foot beyond that line. And that's what your soil pullout, your grid pullout calculation really pertains to. And then lastly, your bulging. This is really characterized by internal compound stability, ICS for short, but this was adopted in 2009. And that Bishop's analysis is really what we're looking at, but all these slip planes have to come through the face of the wall. If any slip planes dive below, that's a global analysis. So ICS is limited only to those slip planes coming through the face of the wall, but that's how we characterize that bulging failure. Maybe we're missing a layer of grid in here, and all of a sudden we've got a slip surface that comes through and it makes a bulge right here in the wall. So all those things are characterized and checked for, in AB Walls design software, which if anybody's interested in getting a copy of that, let us know after the webinar or the presentation. So now, developing your plan for your site. Really, you need to know how tall your wall is, what's above it, types of surcharges or loads. Those surcharges can be a commercial roadway. It could be a driveway, or a sidewalk, a light vehicle load. It could be a generator pad. It could be a foundation of a building. It could be a lot of different things. It could be a surcharge technically can be our seismic load, which we'll talk about here shortly. But then even slopes above. Remember, our slope above increases our Ka value, which then therefore increases our pressure. So that slope above adds a tremendous amount of driving force on our calculations. And then slopes below. The industry really doesn't look at slope below for our internal and external stability. That slope below the wall is really for global stability. So if you have a slope below the wall, the rule of thumb is a 5-foot horizontal bench here. So you want 5 lineal feet flat surface before you intercept the slope. Now you can slope this up obviously to the face, but then that's enough buried block at that point. The NCMA does have a design calculation that you can look up for how tall your wall is and how steep your slope is, and it will give you a design calc for a minimum. But that rule of thumb is that 5-foot horizontal bench. And then we talked about sand and clay, the different particle size, the different, smooth and flat, and differences between those materials. So I'm going to kind of skip through those and talk more about water, because water is really the number one reason why a retaining wall fails. We have to make sure that we route surface water around retaining walls rather than over the retaining walls. The swales and berms above the retaining wall is the navigating water around. And so here, if we were to look at this, rather than having this slope above and having water pour directly over the wall, that we can make sure that we put a swale in to navigate that and bring it really around our site and make sure that it's not poured in. Because if water infiltrates behind the wall, that's something that is a major concern. That's the main reason why walls fail on the retaining wall side. So, Nate, thanks for the note. I'll make sure that someone here in the office touches base there. So, talking about those swales, that can be clay lined, that can be concrete lined, you name it. Other things would be water sources, downspouts, check valves on sprinkler systems. Here you can see they actually routed that downspout into a solid pipe, and they come out through the face of the wall. So make sure that those concentrated point sources are taken care of. And then drainage directly behind the wall. We want to make sure that we vent that pipe out to daylight. This is the old school way. So that old school way is coming through the face. I'm going to show you right here, Wall Drain Pro. is a phenomenal product. It's not an alum block product by any means, but this is actually really only looking at 1.5 inches wide. And it's a small little grate is what you're looking at that then goes back and tees into that drain pipe at the back side. So aesthetically, it looks good. It doesn't require the contractor to cut block, and it's a simple way for daylighting through the face of the block. And why we want to do that is if any incidental water or subsurface water gets in behind there, that adds 1.5 to 2 times that pressure on the retaining wall itself. So we need to make sure that we capture that. And you can capture subsurface water with blanket and chimney drains, like what we're seeing here. So blanket drain across the bottom, chimney drain going up across the back, and that's really that clean stone. So any incidental water or subsurface water that comes in here routes down to the drain pipe and comes out. So if you have water concerns on your site, you excavate in and there's water, make sure that the contractor is stopping and using more clean stone, especially if the design didn't call for this. That would be something to work on immediately. So for the design options, really kind of going around. Poured in place in the 70s, went to precast panels, reinforced soil masses or grid-wrapped walls. These are still used today. Modular block is just really a facing on that soil wrap. It's a higher aesthetic. You're able to go a little bit more vertical, but then it doesn't have that erosion issue or erosion concern that you may have with a soil wrapped wall. And then that other alternatives, masonry reinforcement. So we talked about rigid structures. You can do rigid structures with segmental retaining walls, whether that's a masonry with a full footing that's going down to frost, or if you're looking at like a soil nail earth anchor, you can face any of these types of retaining walls with a modular block to increase that aesthetic. Just to give you an idea, just remember that you have a total wall structure, and that includes batter and geogrid, so that you know how deep into that hillside. And again, AP Walls is actually providing that to you, really built into the program. So that setback chart, to give you an idea, on a standard 6-degree wall, it's very common, you're looking at about 1.25 inches per foot. So this is for a 10-foot high wall. You have about 12.5 inches of batter in that retaining wall itself. So that amounts to a lot, especially if we're talking about that 72-foot retaining wall. That's a lot of batter that's built into there that has to be accounted for during the design process. And then terraces, making sure that you, if that upper terrace is closer than 2H, now most of us here are engineers, so we can calculate that line of maximum tension. We can find how close we can get this upper wall so that it doesn't influence the lower wall. But 2H is a rule of thumb. So this 4-foot high wall down here may actually be designed as an 8-foot high wall, since it's got geogrid running through here, and that upper terrace is closer than 2H. So for instance, on this wall here, these are 6-foot terraces. This bottom terrace actually has 18-foot grid behind it, because it ends up being a 22-foot grade change from bottom to top. Terraced applications might have additional grid, and obviously for global stability. That's probably going to be the ruling factor there. And then with modular block walls, radii, they're going to change depending on product. To give you an idea, alum block classic, which commonly used, 4 foot is the tightest that block can go. So you can get really tight radius out of it, but you have to remember that 4 foot has to be at the top. It can't be at the bottom. So you can't start your wall at 4 foot radius because you lose a little bit every time because of that batter of the wall. So to kind of wrap things up or get things closing up here, I want to talk a little bit about lessons learned on the industry. We've learned from our mistakes. For one, there isn't a fluorescent orange geogrid on the market, and snow fence is definitely not geogrid reinforcement. So this really emphasizes that contractor training, making sure they know what they're supposed to be using on sites. This is kind of the project that everything that could go wrong, did go wrong. This is homeowner, contractor, engineer. He did everything. 12-foot high wall, 4-core spacing. This is actually a pipe that comes in that brings all of the water from his downspouts and including his sump pump from his house. And he brings it right down here to that drain pipe. So he's bringing water into the system, which is obviously a huge red flag. He didn't compact anything, so he actually had an average settlement of 8 inches. And when he had that settlement, now all of a sudden he sheared the pipe. So the next time he had a rainstorm, it ponded above the wall, it poured water in behind the wall. And so now we've got a hydrostatic pressure, and of course I wouldn't be showing you this one without a failure. This is the only project that we've ever seen our shear lip come off. And what happened is the grid actually held up in tension for all that increased pressure, but then all of a sudden the grid ruptured, and as soon as the grid ruptured, it was kind of like it wasn't a slow failure. It was like a bomb going off, and the blocks shot straight out and sheared off that lip. So that's actually the only known case that this took place. So to show you some site pictures, here you can see the block that's still stacked up. You can see 8 inches of settlement. There's the wall and where it failed, going across the city street. And then zooming in on that drain pipe. Here you can see where that drain pipe had sheared off because of all the settlement that took place. And on this, what we had is these strips of grid. And these strips of grid were actually the grid that was sandwiched in between the block, and so that we knew the grid ruptured then before the lip of the block actually failed. So that's how we were kind of able to narrow things down. Looking at an as-built, this is his design as he built it, and this is what the design was that we looked at after the fact. So you'll see that 8-foot grid instead of 6-foot, and then we have 3-core spacing as our max spacing. The big one here, if we look at his calculations, factor of safety for overstress right there at the top, 0.74. So this wall was already failing before it had even settled and got there. It was just kind of a ticking time bomb, where you see that our calculations came out to be 2.18. It's kind of that limiting factor. But these are the things that we really learned and we were able to advance our industry with. So nowadays, if any of you are familiar with bridge abutments, GRS, IBS, you can do a lot with modular block retaining walls. We've talked about that 72-foot high wall. There's plenty of those around the country, around the world. Nowadays we're using our block and reinforcement as a bridge, a single span bridge, for instance. This is actually emphasized from the FHWA. So we're looking at single core spacing from bottom to top. We actually have 4-inch spacing across the upper few layers, so that that superstructure actually sits directly on the soil mass, not on the block, but on the soil. So there's a lot of advancements and understanding of these soil structures that we're using nowadays. If you'd like any more information on this, feel free to email us or almblock.com. I'm going to show you that here shortly so that you've got all those resources. And then seismic. I had mentioned already, we actually did seismic testing, modeled after the Kobe earthquake here that you're seeing. It really decimated in Japan, decimated the entire city. We are still actually the only company that's done the full-scale seismic testing, and we had released that over to the NCMA as a way for our industry to grow again. So here you'll see the block is right down here at the bottom, and notice that you really don't have any settlement here in the geogrid reinforced zone. This is actually outside the geogrid zone. So as soon as you get outside of geogrid, it's no longer holding the soil together, and it's not shaking all together. Now you get that settlement, that consolidation of material in behind that unreinforced zone. So it was very eye-opening to the industry, and again, you can get all of this information directly from our website, including this video. I'm not going to play it here, but we actually have the full seismic shaking on the shake tables, which here's a picture of it that was constructed over in Japan back in 2001, 2002. So plenty of information there. If you're interested in any of these, let me know. But to kind of wrap things up, I want to talk about one last product. It's not Allen Block again, but it's called Sleeve It by Strata, which I have to change the banner across the top here. Strata is a geogrid manufacturer, or a geotextile, and they bought the rights to the Sleeve It system itself, but it's a cantilevered system is what we're looking at, and it's really to resist the load that's applied. So you get that cantilever system, you get this resisting soil mass up here that then resists any kind of overturning for your 50 pounds per lineal foot for railing or small chain link. You're not talking about wind fences or that type of structure, but another great product to have kind of as your background. And then to finish things off, since I showed you a wall that failed, I better show you one that doesn't. This is San Diego Jewish Academy. This is about 55 feet from bottom to top in Southern California, built in the late 90s, early 2000s. Still there today, so if you go down, I believe it's Interstate 5, and look towards the Jewish Academy, you can see this from miles around. About 100,000 square feet, Southern California, so they had a high seismic event. But here, they actually built this upper wall with geogrid reinforcement first, and then they excavated and they did the kind of the top-down approach, and they drilled in or drove in those soil nails. So they built the top first, meaning a little bit different construction. Here you can actually see the top of the wall that had already been finished, and then the soil nails had already been put in with shotcrete facing, and then they're going to come in and put the modular block in front of this. So, Steve, your question on how wide is the base of this wall? I believe, if I go back to my last slide here, they did use an oversized, so they've got 12 inch by 24 inch in the bottom, and then up here I believe this actually went to 36 inches by 12 inches, and they incorporated in a piece of geotextile into the base of that. So, the soil nails, off the top of my head, I'm not 100% positive I know that answer. This case study is on our website, which you can navigate to and see the full write-up and more technical information. But yeah, I apologize, Steve, I don't have the answer for how deep those soil nails went. So finishing this off, a couple last pictures. That San Diego, or the Jewish Academy, was actually right at the base of the wall. It was actually, the foundation of that building was 4 feet from the wall. And then they did put these planter areas in to grow, ivy and something green along the face. If any of you are from Southern California, or if any of you have traveled to Southern California, you don't get rain very often, so it's, I believe, I haven't been out there, but it's still brown, I believe, today. So great thought, but it just didn't pan out with the vegetation. So I had already mentioned our website. We have plenty of information there, whether those are project pictures or case studies, producer information, AutoCAD details, electronic literature. Everything is on our website as a resource to you, including our, you can request a copy of our design software, currently AB Walls. And really this is a user-friendly software that's free for engineers. So feel free, if you don't have a copy of that, like I mentioned, go ahead and request that on our website, and we'll make sure that we get a copy to you. You can do elevations, multiple cross sections, plan view. Here we're looking at the section calculation screen, running ICS, your Bishop's analysis, but then getting into the estimate, material estimate on that project, then the export functions. You can export to a submittal drawing, you can export to a shop drawing in PDF, or you can also export this to AutoCAD. So you have full calculations or full profiles, geogrid locations, everything drawn to scale for you. So definitely a good tool for your toolbox, I'll call it, especially on the design side. John, you asked, you have an older version of AB Walls. Does the current one have global analysis? AB Walls still does not run global analysis, but the AB Walls 15 version, the current copy, does export to a RESA file, the RESSA RESA program, so which runs global stability. So it does export everything into RESA that you can import in and hit calculate to check your wall for global analysis. And that is in the current version. So if you have AB Walls 10 as your old version, we can use those same ID numbers and make sure that we get you updated to the current. So, but that's kind of where I'm going to leave things. I'm going to stop right here on another case study, which is DePauw University in Greencastle, Indiana, is where this project is. Again, there's a lot of resources here for you. I'll open things up to questions if you had anything left there that somebody had been holding. But overall, again, I had mentioned use our office. There's 5 engineers here in our office that at any given time you can pick up the phone and talk with one of us. We've got plenty of experience levels here internally. So there aren't too many retaining walls concepts that we haven't seen before. To give you an idea, and what I'll be doing is I will be following up with an email to each of you. I had mentioned earlier that as soon as I end this event, you'll actually get a pop-up on your screen for the evaluation form. If you want that continuing education credit hour, fill out that evaluation form and then email it back to engineering@allenblock. Otherwise, I will be sending a follow-up email tomorrow with the video and some supporting documents, and I'll also have that evaluation form there. You can send it directly back to myself. So the question about could you talk about crest toppling in the upper 2 feet? That crest toppling is really looking at how I refer to it as localized overturning. You know, the upper 2 feet or the upper, typically you're checking above the upper layer of grid. So if that wall is 2 feet tall above that upper grid, we do look at in the design software. NCMA does it as well. Allen Block design software does it kind of behind the scenes, but it checks for that localized overturning, that the ability for that top 3 courses to, well, topple over, or your crest toppling calculation. So in AB Walls, it's going to pop up and warn you if that's exceeded, but that is kind of a secondary check that I didn't talk about today. So thank you for asking the question. Outside of that, I want to thank everybody for attending. I appreciate the time that you took here, and I'll answer your question here, Nathan. That best practices for segmental retaining walls. You'll see some emails coming out from that, obviously the week of, but feel free to sign up for it in our technical newsletter if you have that in your inbox. So. Nathan, you asked about does AB Walls have the intention to incorporate AASHTO design methodology? We do not, and where we're at, we most likely won't be incorporating AASHTO into the design methodology. It's a completely different concept there, but because the methodology is completely different than like the NCMA, which that's what our industry really kind of pushes for or follows. But we do, here in the office we have other design software that if you have a project, typically what we're looking at is doing the design, cross-section design in like MSEW, for instance, and then incorporating that information into AB Walls to push it through. So, Bob, you asked, could you talk about tamping backfill in the wrong direction? I gotcha. So, yeah. So typically on the construction side, if anybody does need to go, I'll definitely let you log off. But if you want to stay around for the conversation, you're supposed to. The contractor is supposed to backfill and compact, and they're going to compact in parallel paths running away from the wall. So they do that so that they don't bring that dynamic force towards the retaining wall itself. So for instance, if you're going perpendicular to the wall, that piece of machinery could come up and make a turn, and upon doing that turn, you're driving all that dynamic force right to the wall, and it can actually bow out, your upper 2 or 3 courses where you're turning around. So oftentimes that's a constructability issue. So the industry recommends running that. Really, you should only be using a hand-operated plate compactor within the first 3 feet. You're running that plate compactor parallel with the face of the wall, and then working in paths away from it to make sure that you reach your proper compaction or consolidation. So, no. Thanks, Bob, for the question. But if there aren't any more questions here, I'll again thank everybody for attending, and feel free to catch our next webinar series here in August. So, thanks everybody.